Let's start off by defining a set. It is a collection of things or items separated by commas and enclosed in curly braces. This is a set of letters. This is a set of numbers. I can now count the items, usually called elements of the set. 1, 2, 3. If I want to compare the size of two different sets, it is sometimes convenient to pair up elements or groups of elements in each set. So, one pair, one pair, one pair. If I compare them with one-to-one correspondence, I can say that the sets have the same size. Let's compare two infinite sets. These dots just mean I've missed out a few elements, or quite a few in this case. The second set is the set of all even counting numbers. Now I compare the elements. Since I compare the elements up, the two sets must be the same size. If you feel uncomfortable with that idea, then, well, clearly you don't understand infinity yet. Let's consider another pair of sets. We'll stick with the set of all counting numbers, but this time we will compare it to the set of squares of counting numbers. So again, I can pair up the elements. And prove that each set has the same number of elements. This is standard mathematics. Galileo was doing this exact procedure 400 years ago. If you can't grasp this simple concept, then maybe mathematics is not for you. Except I can see something is bothering you. You know deep down that there are twice as many counting numbers as there are even counting numbers. Something is wrong. Let me offer you a different way of looking at this problem. Let's look at two finite sets of counting numbers and even counting numbers. Now we can pair them up. 2 from one set, 1 from the other set. And every time we increase the endpoint of the sets, the ratio of elements stays as 2. So when sets become infinite, the ratio is still 2. I bet that makes more sense to you. Next, we compare the set of counting numbers to the squares of counting numbers. This one is more difficult as we can't pair the elements up, but we can still count the number of elements. So this one has 10 elements. Both end at the same point. The rule is that they're always the square root of the number of elements in the set of squares. So this is square root of this. It's always a much smaller set. Where Galileo went wrong was that the two sets were not being compared in the same way. You should be able to compare finite sets and then extend the endpoint to infinity. Instead, what he did was to compare sets with different endpoints. Infinity should behave in a simple way as a limit of a finite set. So I present you with a new way of thinking about infinity and counting to infinity. First, I'm going to define a new symbol, the Greek capital letter phi. This is defined as the count, so the number of elements in the set from 1 to infinity. Next, there are rules that need to be followed when dealing with this symbol, the phi rules. If you add any finite constant to phi, you just get phi. If you multiply phi by any constant, that's a valid thing to do. It behaves like a normal number. If you take powers of phi, the biggest power wins. Phi squared is much bigger than phi, or any multiple of phi. And by the same rule, This is the same rule. Square root of phi is much smaller power than phi. And you can create powers of phi by multiplication. Just like ordinary maths. And you can divide phi's. So phi is behaving as a very general sort of number, and the only tricky bit is these things where you can add something to it and it disappears, or that the bigger power wins. And those are the phi rules. And if you use the phi rules, there's no magical or mystical properties. You just have to count sensibly.